I'm Frederick Rawlins, the System Security Lab at Oxford, speaking on behalf of the team with Richard Baker and Ivan Martinovic on death by 1,000 COTS, disrupting satellite communications using low Earth orbit constellations. So our motivation for this research is the so-called new space revolution, putting thousands of new satellites into low Earth orbit constellations. Very fittingly, as of about 15 minutes ago, there was a new Starlink launch, so they're currently coasting into orbit now. So bear in mind, some of the figures in this paper are currently now in error. There is a growing use of commercial off-the-shelf software and hardware, which is familiar to and accessible by malicious actors. And it's important to explore what threat new constellations pose to existing satellite communications infrastructure compromised. We have four main research questions. How much interference can different low Earth orbit constellations generate? How is interference affected by the relative location of the receiver and the orbital inclinations? Which of the current or planned constellations would be most effective at interfering with geostationary satellites and therefore appealing to target of cyber attacks? And how are different legitimate uses affected? So we looked at a number of different low Earth orbit constellations. The Planet Labs Dove constellation, which is used for Earth imaging, an example CubeSat Walker constellation, and then two forms of Starlink and OneWeb in their sort of two different phases, comprising of a number of different satellites and shells. We can also see here Inmarsat, which acts as our sort of victim system, which is in geostationary orbit. So to get a feel for some of the constellations, here we can see OneWeb phase 1 on the right and phase 2 on the left. This is now on the right, Planet Labs with their sort of ring structure around the Earth for continuous Earth imaging. We've got Starlink on the left and Starlink phase 1 when they complete their 4,500 satellite constellation relatively soon in the next few years. And finally, a demo Walker constellation that we model as well. So this is a physical layer attack, which consists of disrupting the status quo of satellite communication, in which satellites with low angular separation between sort of victim systems and receivers are purposefully disabled to avoid causing interference. So in our attack scenario, we see an override that disables this or sort of re-enables this small angle satellite broadcasting. We see deliberate matching of known frequency band where that's possible with SDRs. We're broadcasting additive noise across the constellation, and we also accumulate these weaker, but as we will see, potentially still relevant off-angle signals from the further out satellites as well. So what is going against these geostationary constellations? Well, one of the key constellations we look at is Starlink. So we can see that these are considerably smaller than the geostationary Global Express and also considerably weaker. So obviously the decibels is a logarithmic scale. So it's about 4 orders of magnitude weaker. It is, however, substantially closer to Earth. And so when you consider free space path loss, it starts to get a little more competitive. We also have sort of a similar difference in order of magnitude again between a standard CubeSat and the Starlink that we're considering. I'll also note here that we've taken deliberate from regulatory filings to determine the Starlink and Inmarsat Global Express power. Where there is ambiguity, we've favoured Inmarsat to try and make the jamming sort of as hard as possible for the low Earth orbit constellations to give us a low baseline for jamming and hopefully at least for our research, it's more feasible. So our threat model consists of either a launch, which provides you with a chosen orbit, and obviously you can skip the initial sort of compromise vector for your low Earth orbit constellation, or alternatively, a malicious attack against an existing constellation. The victim here is considered a legitimate user of a geostationary satellite, who might be, as we can see, sort of downloading payload data, voice over IP, streaming, browsing, or in remote locations receiving alerts or updates. The attacker here is trying to disrupt those legitimate activities as much as possible. This is both disrupting the signals themselves, but also forcing the receiver to adopt a more conservative broadcast, so relying more on error correction and thus reducing bandwidth as well. We can see in the threat model that we consider a number of different actors in this, ranging from sort of nation-state, military and intelligence agencies, all the way down to individuals and activist groups who have a number of different ways of potentially compromising and affecting geostationary satellites. Everything from launching their own to trying to tamper with one in space, or as we will see, potentially more effectively, insider threat or ground station compromise. So sadly, we do not have the ability to test on our own in-space constellation, and so we are resorting to orbital simulations and RF simulations. Most of the existing literature with interference uses probabilistic Monte Carlo approximations to determine how often jamming might occur, which is quite effective, but it misses out some of these interesting structures and the periodic nature of lots of the jamming that we will see. So we adopted a discrete time step simulation, which considers periods of 10 seconds as all of these satellites propagate through their orbits. Simulation looks something like this. For an example, Walker constellation, we can see a demo ground station there with a cone which dictates all of the satellites that are currently visible to it with given antenna settings. We check only the satellites that are in view. We measure the azimuth and elevation, which are what dictates the receiver gain based on the antenna profile. We run this for 24 hours, and then we export it for RF calculations, which consist of free space path loss using the regulatory emitted radiation and the determined receiver gain to come up with some measure of received interference and also received signal in the case of Inmarsat. So when we come to our actual evaluation, there are a number of caveats here of what we actually mean by jamming. So here that is defined as bringing the signal to noise and interference ratio below 10 decibels. This is an initial coarse estimate for what might classify as degraded service, and in real life this obviously varies massively between systems. We've chosen it here as a coarse estimate, and it allows us to have a consistent comparison between the constellations. As I mentioned before, the legitimate receiver can also change the modulation and coding to try and improve reliability at the expense of total throughput. So again, this is not blanket denial of service, but it should give some measure of degradation. So mean time jamming here is just the percentage of the time over 24 hours in which the victim receiver has a signal to noise interference ratio of less than 10 decibels. And the mean period of jamming is, across all instances of jamming, the average number of seconds where it remains consistently below 10 decibels. So this corresponds more to the sort of denial of service idea rather than just spikes of lost packets. We can see that the Dove and CubeSats are simply not powerful enough at any point in their orbits to initiate what we would consider jamming. With Starlink, we start to get towards the occasional peaks that over time, peaks in interference that bring it below this threshold. But it isn't really until Starlink phase 1 where, on average, we are effectively jamming this system. Or at least that ends up being our mean signal-to-noise interference ratio. And we're getting sort of 40 seconds periods of jamming. Once we start getting to OneWeb and OneWeb phase 2, this goes up a lot. We can see in OneWeb, in the case of OneWeb phase 2, we are jamming more than 3/4 of the time, and for kind of multiple minutes. So an example of what this actually looks like, here we can see a couple of things. So this is over the course of 24 hours, each of these plotted as 10-second intervals. And it is very spiky, which means that we have very little prolonged jamming. This effectively corresponds to the point at which you are fortunate enough to have a Starlink going directly over the receiver, where it has the highest chance of interfering. We also see that the difference between a single satellite jamming in blue and the combination of all of the relevant satellites in the constellation is very small. So those off-angle satellites are contributing not very much at all. And this has to do both with the relative power of the systems, but also the fact that even though Starlink is very dense compared to every other constellation, it's still not dense enough that while you've got one satellite overhead, you're not gonna have anything else that is particularly nearby. We move over to OneWeb, and we see that it is much more periodic. This corresponds to the much more polar inclination of their orbits. So rather than Starlinks that you can imagine sort of whizzing across the sky, you will have a line of OneWeb satellites sort of coming over you in order. And while that line passes over you for as long as that lasts, you get these sort of large spikes in interference. But the rest of the time, there is nothing even remotely overhead, and the system is not disrupted at all. In OneWeb phase 2, as they start adding additional shells, we can see that the periodicity increases, and we can also see that all of these satellites that are off the main angle are starting to add up as well. So at best, they have a 5 decibel sort of improvement over just having a single satellite. So we can see that density actually starts to make a real difference. Even if all of these satellites are off angle, the receiver gain is not nearly as high. We're still getting some impressive jamming here, and some much longer runs of jamming as well. Finally, looking at our CubeSat, this is already idealized for a number of reasons. We're assuming 6 decibel watts of ERIP, which is very high for a CubeSat, and we're assuming that it can disrupt global express at all, transmitting in the KU band, which is currently not the case. Almost all CubeSats do not transmit in KU or KA, and at no point does it come even remotely close to having an effect. So another useful way of looking at this is sort of how powerful would each satellite have to be to make a difference to jam seriously. And so what we can do here is plot the ERIP of each satellite against a number of example ground stations. Here we've used the AWS ground stations just to cover a number of latitudes. These are obviously not representative of the general geostationary receivers, but it points out some interesting things. So this is for a Starlink-like constellation, so following the same number and orbital inclination. And we can see that Sweden is significantly sort of easier to disrupt than many others. And this is because it just sits near the inclination of Starlink. So they sort of bunch up at the top of the kind of sine wave of each of these orbits. So you have many more in nearby to offer jamming here. Finally, on the effects, we can see that it's much more likely to disrupt things like streaming and playing games than it is for more asynchronous tasks like browsing or messaging, and voice over IP falls somewhere in the middle. Finally, on mitigations, there are a number of things to try and mitigate these effects. Obviously, the biggest one is to try and avoid having these constellations compromised at all. So, as in the case with the European Space Agency and launching for the American government, there are a number of pre-flight cybersecurity assessments and certifications. We haven't seen these necessarily reflected in all commercial launches, and so it will wrap up the responsibility of a number of nation states to ensure that these certifications apply there as well. And to minimize harm, the biggest improvement that we can see is narrowing the antenna gain pattern, which makes these sort of off-angle satellites much less effective. And frequency hopping, which can become slightly difficult with highly regulated bands where you have less of an ability to hop to other bands. So yeah, limitations for future work, more representative ground stations covering shipping routes, more realistic receiver antenna gain patterns, and exploring some other feasibilities. I think that is time for questions.
I just wanted to come back to the topic of low-hanging fruit, which was very well introduced before. Today, a lot of these, so this work I think is very interesting, will become even more interesting and relevant in the future, in the sense that at the moment it's not the lowest hanging fruit, but it will become maybe one of the only ways to jam some future systems. Because today, what you see in terms of jamming attacks is often that you jam the uplink, because the satellite is a transparent reflector in a sense. So it's much more efficient to jam the uplink than to try and jam the downlink. But in the future, communication satellites will actually then have regenerative payloads where they generate the signal. So that means that the satellite can already act against the uplink jamming because it does signal processing on board the future satellite. And also for GNSS, I found it really interesting that in LEO, there are many satellites that need GNSS for precise positioning. For example, satellites that measure properties of the Earth, or so they really need meter accuracy precision. And these are difficult to GNSS jam from the ground because their GNSS antennas are pointing upward. So if you fly above them, you can knock them out, whereas it's difficult to knock them out from the ground. So in this sense, this will become very relevant in the future.
Do you have any idea how to get this out of simulations, or at least into some sort of practical settings? Maybe not with constellations, right? But with some toy examples or...
Yeah, so I mean, obviously one of the most effective ways to try and test this out is to do some ground-based examples of this sort of multiple low-power transmission with trying to disrupt high-power transmission. Also, from a space-based perspective, obviously, we as sort of a research community, it gets much more difficult, but the people putting constellations up are having to justify disruptions to a number of governments, and so will have much more extensive, currently private, but at some point sort of hopefully more widely distributed research on exactly how effective some of this off-angle disabling is, and also how effectively you can coordinate that. Obviously, as you get more low Earth orbit satellites, but also more geostationary satellites, it obviously gets a lot harder to sort of constantly flick on and off and measure whether exactly you're in the way of someone. And particularly if you're across nationalities, you can get people sort of asking why they should disable their service to avoid jamming someone else. So yeah, I think on the corporate side, there is lots of interesting research that'll be happening and I hope becomes more widely available